Hi, these two things are identical. I bought this one a long time ago, 6 months ago or something like that. And then I found this one approximately 2 weeks ago, and I paid this one 4 or 5 euros or something like that from a UK seller. First, I will do a teardown of one of these instruments. I hope that one at least is in working condition. We can see the hidden plate of this instrument. This thing is supplied with 28 volts DC. Consumption is 10 watts. And this was manufactured in 95. You can see some stamps here. And the second one is the same. There is another hidden plate here. So let's open one instrument to see what is inside. For example, this one here. Okay, so we can see the construction of this thing. So there is one board here with a daughter board on the top. We'll remove also the front panel. Okay, so we can see first the air pressure sensors. They are more or less identical, except that this one is a differential air pressure, and this one is an absolute air pressure. So this one is used obviously for the altitude, and the other one for the airspeed. You can see that the static pressure is common to both sensors. So the sensors are manufactured by Honeywell, as indicated, so the dead code 99. And there is a pin out of the connector here, so the output can be analog or also digital using an RS-232 or 485. So this seems to be a small power supply, a small regulator. There is a TC962. Some op-amps. This is a classic TL074 in plastic package. This is an AD584 in plastic dip. An LTC 1222. And another quad op-amp here, 74. One LM292 2924. Sorry. These are fit-through capacitors for EMC filtering, so I guess that the input power supply is between these two terminals here. And we have some markings also on this connector. That's interesting. And there is a second board here, which is full of SMD parts. So this is the main processor and the only processor, I think. So this one is an ATC 186, so an Intel processor, 16 bits. This is flash memory. And this is the SRAM. There is an AD524. An LTC 1278. This one I don't know. This is maybe the ARINC interface IC. And we can find also some kind of optocoupler or something. AQW, so this is a static relay. We have 5 of them here. And the crystal is 40 MHz. It is not a crystal but an oscillator actually. Okay, so I have connected this test clips to a 28 volts power supply. I have limited the current to 500 milliamps. I'm going to turn on the power supply. Okay, the current is 220 milliamps. First I will check some power supplies. So I have a plus 15 volts here. The actual voltage is 14.8, minus 15 is minus 13. There is a reference voltage of 2.5 volts. So this one is exactly 2.5005. There is also 28 volts DC 2794. So this is the input voltage. And there is also a 5 volts reference here, which is exactly at 5 volts, 5.0038. There is a minus 5, which is at minus 4.93. 5 volts, which is at 4.92. This is the ground, and this is the flag, which is at 0 volt, and the plus 15 volts X, which is at 13.3. So the 15 volts is a little bit low. I don't know the tolerance of this thing. So next step will be to check with an oscilloscope if you have some signal at the output. Okay, so I have connected the probe to the oscilloscope. I'm going to turn on the power supply again. And I will check if I find something on one of these terminals. So on that line, we have a voltage of 28 volts. So this is obviously the input power supply. Here there is a voltage of 2.5 volts or something like that. There is a discharge, so there is a coupling capacitor on that line. And here we have something interesting. So this looks like an asynchronous signal, and probably with an RS-232 interface. Okay, we can see later. So this is another signal. It seems also asynchronous, with approximately 100 microseconds per bit. So this should be a UART interface at 9600 baud. Okay, so this thing is better. So this seems to be an ARINC interface. Okay, so this thing is alive. Unfortunately, I cannot decode this information, but it should be possible to send these data to an indicator. Okay, so this is another UART interface. There are several UART outputs on this device. This is another ARINC interface, so probably the opposite signal. The other one was just here. You can see that this is A and B, or vice versa, I don't know. Okay, so there is only one ARINC output and several UART interfaces. I have found on internet this small module, which is an ARINC 429 to USB converter. So it's not very expensive, it is around 50 euros. This is a data sheet. You need a terminal on your computer. There is a decoding of the label and 24 bits data, and also the timestamp. We can see on the screen all the data which are transmitted from the AirData computer to the PC. You can make a break. On the first column, we have the timestamp in second. On the second column, we have the label and the data on the last column here. For example, we have the label 203 here, which is the pressure altitude. We have 205, which is the Mach number. We have 206, which is the computed airspeed. 210, which is the true airspeed. And we have 203, which is the barometric altitude. 204 also. 204 is the barometric corrected altitude. 211 is the total air temperature. And we should have the static air temperature, which is 213 normally. Yes, here. On the right of this page, I have written a small decoding function for the total air temperature and the pressure altitude. For these two datas, the datas are coded in binary format in 2's complement. So this is the signed value. But depending on the label, you should have a different number of bits which are used. So for example, I just need to perform a copy and paste. So for the total air temperature, I have done a small reverse engineering. This is on this page here. I have noticed that at pin 17 there was a voltage of 5 volts. This pin is connected to the 5 volts reference using 499 ohms, and I have found also that the temperature depends on the voltage which is applied on that line, pin 12. So I think that the sensor should be connected between pin 17, which should be also connected to pin 12 and the ground. So I have connected a resistor box between pin 17, which is connected to pin 12 and the ground. So currently the resistor is at 500 ohms. I just have to make a copy and paste for the temperature, which is the label 211 here. So 211 is this one. Okay, and you can see that we have the temperature which is indicated here. Okay, I can change the value of the resistor, for example 400 ohms. I can make also a filter on this particular label. So I just need to enter L plus the label 211, and you can see that now only the total air temperature is displayed on this terminal. So now I can copy this thing. Okay, and there is another temperature. I have also written the decoding function for the pressure altitude. The displayed altitude here is in feet. Okay, the label is 203. Okay, you can see that the throughput is larger than the temperature. Okay, so the altitude is 655 feet. The pressure is 0. Okay, I can change the pressure. I have connected the static input pressure to an air pressure generator. Okay, so we can see the change on the data. Okay, the pressure is currently minus 374 bar. We'll wait for the stabilization. Okay, so you can see the higher altitude, 13,000 feet. This was a quick test concerning the ARINC 429 interface. It can be interesting to connect this air data computer to different indicators using the ARINC interface. Thanks for watching and see you next time. Bye bye.